Well, thank you very much, Professor Shankar Dey. And let me begin by thanking the organizers of this, this conference for inviting me to make a presentation on some recent work of ours. And it's really been a pleasure to meet many old friends and, and people who are active in this field. So, yeah, the title of my talk is Quantum Annealing, a novel tool for quantum metrology. So let me first explain the context. Well, we all know that there have been remarkable developments in quantum computing in the past few years. And being an atomic physicist and having tried to do high precision calculations and collaborating with outstanding experimentalists who do high precision measurements, I began thinking if or when quantum computing can become a tool for high precision computations, and by that I mean a novel tool for quantum metrology. Well, as you all know, the conventional kind of quantum computing, which is called universal quantum computing, which is gate-based, has, of course, made important progress. But in terms of accurate calculations, it still leaves a lot to be desired. And you have the coherence and all kinds of noise, which limits the accuracy of computations. I mean, having said that, I must add that not too many atomic calculations have been attempted on a quantum computer, very few, actually. So a bit more on, well, quite a bit more on molecules. But the focus is not on accuracy, but in improving the algorithms. But if you look at the quantum computing picture worldwide, the focus is on what is called quantum advantage. That is speed. That is problems where you can do a calculation on a quantum computer in less time than in a classical computer. But any computer or any computation has two important attributes: accuracy and speed. So I have been a minority in thinking about the accuracy of quantum computers. And the main focus of our research at our center and my collaborations with colleagues in Japan and in the US has been on gate-based quantum computation. But what at least I have realized over the years is that a quantum annealer, I mean, which is the second approach to a quantum computer, you have two kinds, gate-based and a quantum annealing quantum computer. The difference is that a quantum annealer is made up of only qubits and not quantum gates. And the gate-based, as the name suggests, has both qubits and gates, you see. So, it's true that quantum annealing is restricted to a certain class of problems, optimization problems, but there are many, many such problems in physics, chemistry, the whole field of sciences, as well as in the real world. So one of the advantages is that you look at only ground state problems. So the decoherence would be much less, or we'd expect it to be much less. And because it's not based on gates, you don't have to worry about errors arising from gates, you see. So, and I mean, it is by now the consensus of opinion that a quantum annealer is less prone to errors than a gate-based computer. So we wanted to test it out, and fortunately we had access to the D-Wave quantum computer. through the Ministry of Electronics and Information Technology of India. So that's the context in which this work has been carried out. So we actually looked at an atomic problem, a non-trivial atomic problem, to see how accurate the quantum annealing computations are. Okay, so these are my collaborators. The person on the left, the first person on the left, is the student who actually carried out these computations. And then we have 4 people from our center. And then we have Dr. Sugisaki, who is in Keio University, one of the leading centers in Japan for quantum computation. And we also had some interaction with Dr. Ken Dial, who's one of the pioneers of the relativistic quantum theory of atoms and molecules. Okay, I'll give an outline of the talk. So because we're applying quantum computing, or in this case, quantum annealing, to atomic systems, I thought I'd just give you a brief introduction. And this means both neutral atoms and atomic ions. And so there are both. So if you look at an atom or an ion, you'll have relativistic effects, and the atoms become heavier, the relativistic effects become more important. And then you also have mean field and correlation effects. So one has to compute these 2 effects accurately to get an accurate result. Now, the problem that we're looking at is the fine structure splitting in atomic systems. This is the splitting between certain energy levels, that is, the L, the orbital angular momentum, and the spin angular momentum are the same, but the J value, the total angular momentum, is different. So that's the fine structure splitting, and it's a genuine relativistic effect. So those are the first 2 points that I'll just touch upon. Then I'm going to talk about the basic ideas of quantum annealing, not quantum annealing on the whole, but quantum annealing with reference to the D-Wave hardware. Now, the D-Wave company in Canada built the first quantum annealer. Actually, it was the first quantum computer of any type. I mean, at least commercially, it was the first quantum computer. That was in 2007, and now it's being widely used. Okay, so we want to use the D-Wave machine to calculate the fine structure splitting. And obviously, we should have some kind of a quantum algorithm. And the quantum algorithm is a quantum annealer eigensolver. I'll talk about that. And this is meant for computing the ground state energy of atomic systems. So the fine structure is 2 levels, the ground state and the excited state. So we've used atomic symmetry. So we have taken advantage of the fact that the atom has angular momentum symmetry to also calculate excited states. Okay. And the specific system that we've applied to are boron-like ions. So this is the fine structure splitting in boron-like ions. So it has an outer 2p valence electron, and the J value is, I mean, from a relativistic point of view, 1/2 and 3/2. So that difference is what we want to calculate using a quantum annealer, the D-Wave quantum annealer. So just to remind you, if you look at so we have an atom, the nucleus and electrons, and that's the Hamiltonian, as you all know. And for large nuclear charge, large Z, the velocities of the electrons increase, and therefore they must be treated relativistically. For something like hydrogen, it's not really necessary, but for hydrogen like uranium, it's absolutely essential to use relativistic effects. Now, the relativistic effects can be incorporated in the Hamiltonian. So the one body part is the Dirac Hamiltonian with the nuclear potential. And then you have the Coulomb interaction. This is called the Dirac-Coulomb Hamiltonian. Now, the Coulomb interaction is the dominant interaction, but there will be corrections to that because that's the static interaction between electrons, but electrons are moving. And so you will have to take into account the motion of the electrons and the magnetic fields associated with them. And that is done through the two-body part is the bright interaction, which is the leading correction to the Coulomb interactions. Now, there are, of course, other corrections arising from self-energy vacuum polarization, but they're not as important. So in our work, we've included Dirac-Coulomb and bright interaction. And okay, I mean, just to put things in context, how one calculates atomic wave functions. So here, what we do is we write the wave function. The wave function corresponds to a particular value of, this is relativistic, of course, a particular J value, the total angular momentum, M and pi is parity. So these are the good symmetries. And that can be expressed as a linear combination of different configurations. Now, just to give you a very brief example, so suppose if you have the helium atom, the simplest many electron atom. So in the mean field, we consider 2 electrons. So each electron is moving in the potential of other electrons. But then when they start interacting, if you take the interaction between them, then the configuration can change. You can have 1s up, 2s down, or you can have both the 1s electrons getting excited to 2s and so on. So if you have a 3-electron atom, you can have 3 electrons getting excited, 4 electrons getting excited, and so on. So therefore, I mean, the total wave function is a linear combination of all these configurations. So the wave function is a probability amplitude. So these are all possible amplitudes. So you have to add them up to get this. Or in other words, you can think of all these excitations as forming a complete set of basis functions in the many electron space, and you can write it like this. Now, this is called the configuration interaction wave function because these correspond to different configurations. But this has to satisfy the Dirac-Coulomb or the Dirac-Coulomb bright Hamiltonian, and the energy corresponds to a particular J value and particular parity. I mean, M, of course, but the M states are degenerate. So, and this can be either a ground state or an excited state. Now, to find the energy and these coefficients, because if you know the coefficients, you know the wave function. What I think one of the most popular ways of doing it is to write an energy functional, which is this bra psi h get psi, and then you want psi to be normalized, so you impose this normalization condition as a constraint, and then you then this equation, which has that as a trial wave function, reduces to hc equal to lambda c. C is the vector consisting of the coefficients, and so lambda is the energy. So this normalization constant turns out to be the energy. So this is an important thing, that if you want to find the wave function and the energy, and you want the wave function to be normalized, then this condition is necessary, and the Lagrange multiplier is actually the energy. So fine structure splitting corresponds to 2 different J values with the same parity. They have the same L and the L. They have the same L and S. Now, so we'll present results for fine structure for boron-like ions. And the quantum algorithm that we use is called the quantum annealer eigensolver. So the quantum annealer eigensolver is based on this idea. That is, you take an energy functional like this, make sure that the wave function is normalized, and so that you get this equation. Now, you can, of course, diagonalize this Hamiltonian to get the eigenvalues and the eigenvectors. Now, or you can just directly minimize the energy. So these two are equivalent. So in our approach in the quantum annealer, it's not diagonalized, but this is directly normalized. And this is directly obtained by using the variation principle. Now, this algorithm was first proposed in 2019 by Teplukin and collaborators from Los Alamos. And so they have been looking at the ground state energies. Yeah. You mean quantum computers or high performance classical? Ah, yeah, yes, that is true. I mean, therefore, if you have a large system of, I mean, if you have a system which is very heavy with lots of electrons, yes. Oh, sorry. I'll come to this point, okay? Not yet, not yet. I mean, it's very, I mean, at the moment, the regular computers can handle larger systems better than D-wave systems or quantum annealing systems. But work is still in progress on quantum annealers, yes. Okay, so the main objective of my talk is to show that we can get accurate results using a quantum annealer, not necessarily large systems yet, but in the future, yes, there is promise. Okay, so, all right, so so let me just give you an idea of what quantum annealing is in general. So quantum annealing in its present form was proposed in 1998 by Kadowaki and Nishimori. Nishimori is a colleague of mine from Tokyo Institute of Technology in 1998. So what they proposed was that one can use the adiabatic principle or the adiabatic hypothesis to find the ground state energy. So what it is that, so you take a system, allow it to evolve, and the Hamiltonian is written like this. So P as a function of T, sigma these are the Pauli matrices, and H, and then you let the system evolve from time 0 to time capital T. So, and now if the change is done sufficiently slowly, and if the system is in the ground state initially, it will continue to be in the ground state throughout. And at this time T, the final time, you replace the Hamiltonian by the Hamiltonian of interest to you. So that way you will get the ground state for the Hamiltonian of interest. But however, there are many assumptions, which is that the change is slow and capital T, the anneal time is large enough and so on. You see, so this is, so this whole process of going from the initial time to the final time is called the anneal, A-N-N-E-A-L. Okay, so this is, you know, a way of finding the ground state of a system. And so they proposed it in the context of the Ising model, these spins. And then what they found, and it has been subsequently found, was that you get an energy landscape like this. So these big circles refer to not one single spin, but a configuration of spins. So if you allow it to anneal, then so this corresponds to the final time. I mean, you know, so you have to do many anneals, you know, to get the minimum. So at one point you'll find that you get an energy minimum for a certain configuration of spins. So for a certain configuration of sigmas, you'll get a minimum energy. So this
May I ask you a question?
Yeah.
So what I understand from this expression, so P means model space and Q means orthogonal space in that sense, right?
No.
So,
okay. So
initially it was in some spin configurations, that arbitrary spin configuration.
Initial time.
That was maybe that you can call P state or other way.
Yeah. So at time T equal to 0, the value of P is 1 and the value of Q is 0. So the Hamiltonian was initially in sigma x.
That's why I said it's a model space actually. In that sense, it is a model space P. And now I think I got it.
Yeah. So finally, P will be 0 and Q will be 1. But but between 0 and T, the values can change. But if the adiabatic theorem holds, then it will strictly be in the ground state. But you know, that doesn't always happen. You know, I mean, yes, please. Yeah.
I also have a question. So if you have like a classical potential, receiving some local minimum, then shake it a bit, then eventually it will go.
Yes.
The same and
Yes, 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 yes.
So, can you maybe explain
Well, I mean, the quantum effect here is tunneling, you see. So I don't know if you would consider that as kind of shaking. So so if you think of the motion and you think that they're moving across some barriers, then the motion takes place because of tunneling, basically. So that could be, you can think of that as some kind of shaking then? Okay. Yes.
I would have expected that you need some way of dissipation to come there.
Yes.
Is it included? Because tunneling would not be a dissipation.
No, that's true. That's true. So some amount of dissipation is there, but see, it depends on how slowly you change it. There will be some dissipation, but so therefore you may not, annealing may not be, I mean, a single anneal will not guarantee that you've got the proper, minima. So you may have to repeat this many times. So if this is done many, many times, thousands or even millions of times, each anneal time is about 20 microseconds, then yes, you can sort of minimize the values of dissipation if it's done over a large period of time. It is done, so you do a statistical sampling of this. You see. So, so this is the basic idea of quantum annealing, you see. It's based on the adiabatic principle.
Sorry, just one more clarification. Is there any relationship or constant between P and Q?
No. So except that initially P is 1, Q is 0, finally Q is 1 and P is 0. But other than that, like for example, you could think of this as something like 1 minus, P could be 1 minus small t divided by capital T. Okay. So, and Q would be small t over capital T. So they're sort of related in the following way. All right, now, okay, now what is the connection between atomic physics and quantum annealing? That means given an atomic problem, can you map it on to a quantum annealer? Okay. All right, so let me remind you that this is what we did. We minimized the energy with lambda as the constraint. And so if you take the wave function as a linear combination of configurations, then this energy functional will reduce to that. Now, I'm assuming that it is normalized, so that's one. So Hij is the matrix element of H, you see. So you get an energy functional of this kind. So which is, say, Ci square minus Cij. So now, the idea in quantum annealing is to minimize an energy function of this kind. But how do you express this atomic physics problem in terms of qubits? Okay. Now, to do that, so remember that these coefficients can vary from -1 to +1. But they can be 0 to 1 in terms of the absolute magnitude. But qubits can only take two values, 0 and 1. So we have to find a way of changing the decimal numbers to binary numbers, and that is done through this. Okay. So this coefficient C, and so this is done iteratively. So at the rth iteration or repetition, we have something like this, you see. So Q here is only 0 or 1. So these coefficient C's can be expressed in terms of binary numbers, 0 or 1, through this expression. So what we do is that we substitute this value here, and then the C's will be in terms of Q's. Now, when we do that, we get an expression like this. So it was quadratic in C, now it is quadratic in Q, Qn, Qm. And it was, So now when you have Ci square and you express it in terms of Q, because the values are 0 and 1, Q square will be Q. 0 square is 0 and 1 square is 1. Okay, so you get a form like this, and this is just a number. Now, in a quantum annealer, the energy functional F that is used has this form, QII, QI plus QIJ, QIJ. So the D wave is based on this structure. So the energy functional has to be in this form, and this is satisfied by that. So you can see there's a quadratic term and a linear term, okay, and just a number. So what we do is that we do this many, many times. We do the annealing many times. And so this R here corresponds to an iteration or repeat, and that in our case corresponds to 1,000 anneals. So now once we do that, so if you minimize this, then you'll know which combination of Q minimizes this quantity F. And those, say, suppose the configuration is 0, 0, 1, okay? So that means Q1 is 0, Q2 is 0, Q3 is 0, and Q4 is 1. So then so you know which Qs minimize this energy functional, and then from those Qs, we recalculate C, the coefficients, for each iteration. Okay. So, yeah, yes. Excellent question. Yeah, I'm sorry, I should have said that. Okay, now the classical devices calculate the Hamiltonian matrix elements. Okay, now the C's, which are expressed in terms of Qs, that is on the quantum annealer. Because what we do is that we minimize F. And when we minimize F, that corresponds to a particular configuration in the quantum annealer. Bunch of Qs out. That's the quantum device. Yeah. Well, it's predominantly in the quantum device. But anytime we need to calculate the energy that because we want to check if the energy has converged or not. Only for that part, we use a classical device, because the energy has to be, because once you get from the Qs, you get the coefficients that enables you to calculate the wave function. And then once you have the wave function, we use this to calculate the energy. This is the only part that is done on the classical device. But the Qs that you get are from the quantum annealer, which is then changed to Cs, and then you get the wave function, you calculate it. Now this is, of course, does this answer your question? Okay, fine, yeah. So the final energies that we get is after many, many repeats. Okay, so, all right, so this probably will sort of summarize how the calculation is done. So we first construct the Hamiltonian of our choice. This is done on a classical computer. And then we construct the energy functional. And then this is done again on a classical computer. Then it's converted to the Kubo form, because Kubo form is the form that the D wave recognizes. So this is FQ. This is then, once this FQ is constructed, then we optimize it. And that is done on the D wave machine. We use the latest D wave machine, which has 5,000 qubits. Now, I'll not go into the technical details, because when we do this, we have to take into account the architecture of the D wave, where 1 qubit, it's not an all-to-all connection, but rather 1 qubit is connected to 15 qubits. So we sort of have to do some arrangement. I mean, we did not use 5,000 qubits. We used about, in one case, 100 something, in second case, 190, 100 and 200 qubits for the two different states. Yeah. Oh, yeah, sure. So this is the so this embedding is mapping the atomic energy functional to the D wave structure, and then we anneal it many times. And then we get the configuration of Qs. From there, we get the coefficients, and then we construct the wave function, calculate the energy, and then keep repeating till we get the final energy. So, right. So, so we have used this algorithm to calculate the fine structure splitting. Now, there are two states. Now, this, I mean, you know, strictly speaking, this is the ground state, and this is the excited state. So what we did was that we made use of atomic symmetry. So if you take J equal to half states, then this is the minimum energy state. And if we take the 3 half states, that's the minimum energy state. So what the annealer does is that it gives you the ground state energy for the minimum energy state for a set of states. So, you know, we really didn't calculate the excitation and in energy, you know, in what you might call a proper way, but rather we made use of the fact that made use of atomic symmetry to calculate these 2 states. This is the lowest for half, this is the lowest for 3 halves. We did 2 different calculations, and we got, I mean, that means we applied the algorithm twice, and we got the energy for each of those, E for J equal to half and 3 halves, and we took the difference. Okay, now some results. So here, the REL-CI is the calculation done on a quantum, is done on a classical computer. This is the usual configuration interaction calculation in a regular computer. So we have taken 4 ions, boron-like ions, and this is the result from the D-wave hardware. And this is the percentage difference. And this difference is calculated from, yeah, okay, so this difference and that difference in terms of percentage is this, very close as you can see. And the hardware results are also close to actual lab measurements, high precision spectroscopic measurements, you see. So this, so the error on the average is about 1%. In other words, these results that we've got is 99% accurate. Now, I'll have this the last slide. I mean, so we have performed computations of fine structure splitting in boron-like ions using the quantum annealer, and we obtained an accuracy of 99%. Okay, now how did we get this kind of accuracy? One is by including the important physical effects. The bright interaction had to be included because it's a genuine relativistic effect. Now, the choice of single particle orbitals is also important here. Regular Hartree-Fokker-Dirac-Fock orbitals will not give the right values. So you'll have to find a way of using orbitals that are common to both the states. So that is the physics. And the workflow, that is the existing quantum annealing workflow had some limitations. So like in the choice of the initial choice of the coefficients where we used perturbation theory and so on. So and also the embedding, the way so there the student played an important role. We had to sort of adapt the atomic problem to an annealer. So a lot of thought had to go into that. Now let me make contact with this conference. So this is the first step in carrying out high accuracy quantum annealing computations of atomic quantities, which have a wide range of applications, including the probing of new physical phenomena beyond the standard model of particle physics. So this is just a first step. And I think I can now answer a little bit what Subhadeep had asked. So you see, Subhadeep, I mean, what we did here was that we had at our disposal 5,000 qubits, but we did not use more than 200 qubits. But what we made sure is that they were all connected. So through a proper embedding, the important thing is all-to-all connectivity. That we achieved by adapting the existing architecture of the annealer, which is 1 to 15 we sort of embedded that and made it all-to-all connection. Now, these kinds of things will have to happen, a combination of the improvement in physics and adapting it properly to the architecture. And a lot of work is going on in the architecture of that. Now, how long it will take to do high precision calculations on larger systems, that's an open question. But the fine structure interval in boron is not a trivial problem. It was really a very sensitive test of relativistic many-body theory. And in the 80s, in the early 80s, the actual value was not even known. I mean, experimentally, yes, but the calculations were giving wrong results until we figured out the right physics. So I think I should stop now. Thank you very much. Yeah.
Anyway, I'll speak a lot. Thank you so much, Bhanu. Very interesting. I have a couple of questions. One is, could you say a few words about the D-Wave hardware? Is it like superconducting qubits, or and also, I don't know if it is a proper question to ask about the quantum computer. What is the clock speed of this? So I don't know if it's something that quantum computers are also characterized by, but presumably yes.
Yes.
And maybe I ask my second question also. So, okay, so you use now quantum computer to help in this atomic physics calculation, but I didn't quite get how much advantage it gave compared to what you usually do with normal computers, and what is the advantage? What is the prospects of the advantage? So that's my question.
Yeah. All right. Now, sorry, what was the first question? And then,
D-Wave hardware, clock speed, and
yeah.
What does it help?
Yeah, I think this reminds me of what Professor Caves mentioned yesterday. I mean, if you ask a series of, okay, so I'll answer in random order. Okay. Now the prospects, okay. So as I said, there are two important attributes of any computer. One is accuracy, the other is speed. Now, most of the people are now concerned about speed, quantum advantage, you see. Now, without bothering about the accuracy, you see. So we are not really, at least we have not really focused on the quantum advantage part, which is the speed. That is whether a quantum computer can solve a problem faster than a classical computer. That will be of no use if we cannot do accurate calculations. You see. So we focused on the accuracy part. And we found for a non-trivial problem, it is possible to get 99% accuracy on this. Okay, now let me contrast this with a gate-based computer that we've also done. So the analogous algorithm to QAE is called the variational quantum eigensolver. We use that, and the accuracy that we got was about 20%. Now, of course, you have to do a lot of error mitigation. You know, quantum error correction is a long way away. So we did not do, by the way, we did not do error mitigation here either because the results were very good. So error mitigation is a growing field, you know, in this present NISQ era. People are trying to find ways of accounting for errors and so on. So, so I would say that accuracy, if we can sort of have control over accuracy, at least from the point of view of atomic physics or high precision physics, that to me is more important than quantum advantage. Once we have that under control, I mean, I don't know how long that will take, then yes, we have to think of, you know, advantage. Otherwise, why would you use a quantum computer, you see? Yes. Now, at the moment, a classical computer for these kinds of calculations is much faster than a quantum computer. There's no question about that, you see. Right. Now, about did you say the clock time or something? I can't remember. Clock time. Yeah. That I don't know, but when you do one anneal in a D wave, it takes about 20 microseconds. So you have to do many, many anneals in the calculation, you see. So, but yes, to perform this calculation, it doesn't take much time. I cannot remember how long exactly it takes, but it's much slower than a regular classical computer. The results you see are of similar quality, and that's the important thing here. If I'd done this on a gate-based, the agreement would not be 99%, but more like 20% or even less. So the point that I'm making is that if you can express a problem, and which we can in atomic physics or molecular physics, in terms of a variational principle, then you can use a quantum annealer. Now, I'm sort of tempted to say this, that the D wave is the D wave Hamiltonian. It is for the Ising model, where you have, it's like, the sigma z interactions. But the actual atomic Hamiltonian, if you change the atomic Hamiltonian in terms of spin Hamiltonian sigmas, you will also get contributions from X and Y and so on. Now, that kind of work we're involved with in collaboration with a group in Spain, and we've just recently got funded by European Commission for doing this work. There we're going beyond D-Wave. D-Wave is doing remarkable work, actually. So, they've been able to do lots of very nice, computations of spins, spin glasses. They've observed, Kibble-Zurich mechanism and so on, all been in nature physics in the past few months. But it's still, the Hamiltonian is limited to the Ising model Hamiltonian. It's sort of, the architecture is the Ising model. So, but if you have sigma X, Y, and so on in some interactions, like as we do in the atomic Hamiltonian, then I think one has to have a new generation of quantum annealers, which the group in Spain are trying to do. And also groups in Japan, MIT, Berkeley, I think you probably know Irfan Siddiqui, he too is, no, he's not in, excuse me, I mean, he is, yeah, okay. He's not involved in it.
Okay.
But yeah. Just one last thing. I think you asked about the qubits, right? These are superconducting qubits. But in Innsbruck, they're thinking of cold atom qubits. Okay, sorry.
Yeah, okay. We can take another question just from the students.
Hello, sir.
Oh, yeah.
Sir, so in the beginning, you mentioned that we do not use gates and only the qubits, right? So is it a kind of analog type device?
In that sense, yes. Yeah. I mean, if you think of a quantum circuit as qubits and gates, then the gate-based would be more like a digital quantum computer. And this is some sort of an analog computer in that case, yes. But this is not the only analog computer that exists now, but it would be one type of analog computer, quantum analog, yeah.
And sir, one more question. How is it that we are able to use many number of qubits in this type of devices, like 5,000 qubits, but in other kind of system, we are only limited to like a 50 or something like that?
Yeah, I think this has to do with the fact that you don't need gates, you see.
Okay.
So, and partly architecture, but I'm really not competent to answer this question. I'm just an atomic theorist who tries to see what computer is available and do calculations. But I would say that because you don't have gates, that's a simple answer. Maybe there could be other answers. You can have much more qubits. You can use more qubits. But of course, you lose flexibility because you're restricted to optimization kind of problems.
Okay, sir. Thank you.
Okay, maybe you can take it during tea time. Okay. So we go to our next presentation in this session. And first, thank the speaker.
Oh, sorry.
Professor Das.